Now to the learnings. I shortly want to describe the approach we took to prepare this presentation. So you can find many lists online about common issues in the solidity space, also about CosmWasm. But what we tried to do here is we went through all of our audit reports that are all published on our GitHub repository. You can scan this QR code to check them out yourselves. And we used these public reports and took screenshots of all issues, and then we categorized them. So all the critical and major issues were put into categories. And I will now go over the most common categories where we see most issues, and also give you some real-world examples of what went wrong, what we can learn from that. For this whole approach, we anonymized our clients. So these are actual issues from actual audits, and you can probably find out who it was if you wanted to, but we don't want to point fingers at anyone who missed things in their development. So here you find all the categories where we had critical or major issues. And in this talk, due to some time constraints, I can only look deeper into a few of them. So we're looking at logical flaws, at lack of access control, unbounded iterations, sniping, front running, sandwiching, and rounding issues. Here you can see for the access control category, just screenshots of issues from reports. And you can see there's sometimes this a red line. Don't worry about reading them now, but red means it was a critical issue, and orange means it was a major issue. I just put these screenshots here so you can see how often we see access control amongst 100 audits. So you can do some calculation and see likelihoods of running into access control issues. What access control means is you typically want to restrict access to certain functionality of a protocol. And the issues we see is a lack of access control. So for example, an admin function does not check if the user is actually an admin, or an escalation of privileges, which means that someone is authorized to perform something, but they should not have access to other functionality, but somehow they can get access to that other functionality. I share a couple of code examples in this presentation. Don't worry about reading and understanding all the code. I just put them here so you can understand a bit how auditing works internally and how we find these things. So here we have an example with a function to update parameters of a money market protocol. On top, you can see that there's an entry point. And then here, this is the message, the update parameters message. But at the entry point, there's no access control. So anyone at this stage can call this function. Let's jump into the function itself. And we can see here again that there's no access control. So this is quite a trivial example, but what it means is anyone can update these parameters. And the parameters, this is the actual issue from the report, they can be used to manipulate the market. So you have different parameters that can be set here, and hence we classify this as critical. So what do we learn from this? Ideally, if you do authorization checks, do them as early as possible in your control flow. Then it's harder to miss them. And we recommend that teams use the principle of least privilege, which means that restrict access as much as possible. And lastly, to detect those issues, we recommend that teams do test non-happy paths. So often we see test cases that only test if functionality works as intended. But especially with access control, you can easily find these issues before we detect them in an audit if you just write test cases for non-authorized users that should not be able to access certain functionality. Now let's go to the second category, unbounded iterations. And DOS means denial of service. So we see this in lots of audits, in CosmWasm as well as in Cosmos SDK code bases. And we have two screens here with screenshots of these issues. And I will also go into more detail in a moment. But unbounded iteration basically means that a user can input, a user input determines how often a protocol iterates. For example, a user can give an integer value and then the protocol does something, and the integer determines the number of iterations. Or there's a data structure that a user can add elements to, and then iteration happens over the data structure. And the problem is that functions that use user input for iterations, they tend to run out of gas at some point, right? Or they consume more gas over time until they don't work anymore because they will always run out of gas. Here's another example. This is a liquidation function from a money market protocol. And you can see here in line 154 down here, you don't need to read it, but there's an iteration across all unlocking positions of a user. So users can create unlocking positions, and they can create as many as they want. The problem in this context is that this liquidation function is doing iteration. So users can actually prevent getting liquidated by just creating lots of tiny unlocking positions, and then they are not liquidatable anymore. So they can basically game the whole system and just create maximum debt, run away with tokens, and we classify this again as a critical issue. Don't worry again about reading this. I'm just moving a bit faster to save the time of this talk, but happy to chat about anything with you later. Again, what do we learn from this? We recommend avoiding iterations as much as possible, especially if they depend on any user input or if they are unbounded. If you need to use iterations, then please limit them or use batch processing. So allow users to specify how many iterations they want to do in their call and process them in multiple calls. If you need aggregate values, for example, sums of positions in a list, it is normally wise to switch the system into a write-heavy system. So you pre-compute values at write time rather than calculate values by iterating over them at read time. Cool, next category, inconsistent state. This is also something we see often. It often leads to also denial of service. Inconsistent state just means that if you have a protocol, you often have a state machine in the smart contract world. State machine means you have several finite states, so there's a distinct number of states in your protocol, and then you have state transitions between these different states. And what we can often see is that protocols, they can get into a state, but then there's no transition out of this state, and it makes the protocol stuck in a certain state. We don't have an example here for time's sake, but there are lots of examples in our published audit reports you can have a look at. I think this area is very interesting because we don't really see teams addressing this issue. There are certain methods how you can address them. One of them is finite state machine design, which means that you actually model your state machine just in your documentation, or there are certain tools available that allow you to model state machines, and then look at the state transitions and check if there's a way for the state machine to get stuck in a certain position. You can also write tests that explicitly check the transitions between the states, or you can use formal verification to actually check if your model is always holding certain variants and the models are always holding. Now, this category logical flaws is definitely the biggest one. Like of all the critically and major issues, in this category alone, it's probably 40 to 50% of all the issues. So we have one screenshot here, another one there, third one, fourth one, fifth one, sixth one, seventh one. So there's a lot of times that we run into these issues. What are those? This is mostly typical software bugs, right? You have a specification and the code does something different from the specification. It does something unintended. For example, data is not handled properly, like serialization, deserialization mistakes, or the control flow gets into, you have an if-else condition and the condition and the effect are just swapped. So you get the protocol again into a state that's not intended. But also very often, especially around IBC, we see that teams have wrong assumptions about how the underlying system works. That you implement a smart contract that uses IBC channels to run a contract, but you might not consider that there are some IBC entry points that need to be considered, or you don't consider that there's a Cosmos SDK chain underneath that has some limitations or put some implicit limitations to your protocol. Again, some examples here. This one is a function on a streaming protocol that is finalizing a stream. What that means is not so important, but at the end of this function there will be payouts of certain amounts of tokens. So at the bottom of this function you can see that they implicitly have a state machine, actually quite explicitly. So you have a status of the stream, and that status means it's the state of the state machine, right? The state of the state machine can be active, it can be finalized, and there are certain other states. But what happens here is there's a check if the current status of the stream is active, then it will be set to finalized in this line here. So if we go down in that function, we can see that now the transfers are happening. Details are not that important here. But if we jump back up here to the beginning of this function, before the state is set to finalized, there's never any check that the system is not already in the finalized state. So the state is changed to finalized, but it's not checked whether it's already finalized. So it's possible for someone to just call finalized again and again and again, always getting payouts from the protocol, because one condition is missing here. And again, here's the issue write-up from the audit report. How do we deal with this? And since it's the biggest category, I put quite some different points here. Already mentioned finite state machine design before, using specific modeling languages or just documenting it properly. Then formal verification to verify that your model is actually holding under different conditions, and that certain conditions regarding the model do never break. Rigorous testing. There's something called system testing, which is specifically checking the state machine and whether the transition is all implemented properly. Then testing of edge cases. We often see, as I mentioned before, that teams are just testing happy paths, but not what can go wrong if someone's sending a zero transfer, for example. So it's very important for preventing these logical flaws to also test the cases that are not on the happy path. And then making sure that you understand the assumptions of the underlying system. So for the IBC example from earlier, for IBC connections between contracts, CosmWasm smart contracts, there need to be 6 entry points implemented. And sometimes teams do not implement some of this functionality correctly. For example, there's an entry point for closing a channel, and if you don't consider that option, then it might be the tokens are locked on one end of this channel. And then lastly, end-to-end tests can be very important to uncover these wrong assumptions about a protocol. Ideally, these end-to-end tests, they run as close as possible to production, so on a deployed testnet somewhere, or just a test deployment on mainnet. And these help you to check if the system behaves not just in unit tests and in concept, but also in practice, as expected. We have 2 more categories. This is the second last one that I want to talk about today. It's related to sniping, front running, and sandwiching. These are common terms in the crypto world. Just quickly to explain what it means. Sniping means you do something quicker than another person, and you basically get whatever they wanted to do first. Front running is similar to that, and sandwiching means that you inject a transaction before another transaction and after it. So you basically wrap it with your own transaction. How does this work? You can either pay more gas on Ethereum or give tips on other ecosystems in order to be faster, to be prioritized in the mempool before the target transaction. Or even better, if you are a validator and you produce your own block, you can just inject your own transactions in the right places. This is often referred to as MEV, and that we order the mempool in order to extract maximum value from transactions that are in the mempool. And there are some designs that are very susceptible to sandwiching and to losing value because you don't consider that there can be sandwiching. So to go into a practical example here, we have a contract that has rewards. I think this is 75 protocol, but there's some rewards set up. And these rewards are always swapped to the right token, to the reward token. But the rewards can accumulate in different token denominations. And you can see here in the bottom of this function, there's a swap call to osmosis. And this swap call is actually not setting a min output amount. So it's implicitly set to 0. And even actually the development team even put a to-do here. They said implement slippage tolerance. Sounds like a small thing to change, but in actuality, if there is someone applying MEV, or if there's some front runners active, some bots that detect transactions such as this one, they can cause a big financial loss for the party that's sending this transaction. Because what will happen is, if you know that there's a swap coming and someone is buying a token, you can just jump in right before that, buy that exact token, buy a big amount of it, so the price changes, the token gets way more expensive through the action. then the target user here, or this call here, is also buying the same token, drives the price up even more, and then you sell the tokens you bought before for a higher price. So make riskless return. Again, this here is the from our audit report, the issue description. And in this case, the sandwiching attack is even worse because the swap asset function I just showed you, that's permissionless, so any user can call this. So malicious users, they cannot just wrap you, but they can actually just send free transaction. One buys the token, one does the swap, and the last one is actually selling the token again. And you can do that repeatedly to drain the whole protocol of funds. What did we learn from this? Generally, we have public unencrypted mempools on most blockchains, at least the ones where we're active. So anyone can observe and front-run any transaction. So it's important to be aware of this and make sure that your entry points, your functionality is not too susceptible to any front-running. There are different mechanisms how to do this. Happy to go into more detail after this talk. And if you're dealing with automated market makers or other DEXs, be very aware that if you don't set any slippage tolerance, and if it defaults to 0, or if you set it to 0, then you're very susceptible to anyone extracting maximum value from you. And there were actually cases in the Ethereum world recently where someone swapped token amounts and they lost more than 90% of their value because they didn't protect against slippage. Last category for today, rounding. Does not happen that often, but sometimes there is rounding in protocols in favor of users. And this makes a protocol susceptible to something called skimming, when a user can send many small transactions, but the protocol always rounds in their favor, so they can get higher token amounts from the protocol, or they can maximize voting power, but just instead of sending one big transaction, sending many, many small transactions. Even worse than that, if rounding is implemented in protocols, it can break invariance. So for example, if user balances are rounded up by accident or explicitly by purpose, and the total supply, for example, is not rounded up, then the sum of all user balances do not match the total supply anymore. And in these cases, it can actually break the whole protocol and it can get into an inconsistent state again. So let's look at an example again. This is actually from a automated market maker, a swap function. And the swap function is taking two different pools of tokens. So what the balance is in the AMM, the liquidity at that point when the function is called. That's the offer pool, the ask pool. And then an amount of tokens is sent into the swap function. There's also a commission, which is not really relevant for this example. And if you look now in line 743, there's something happening that we call integer floor division. What it means is if you divide integers by with each other, you can have a remainder, right? If I divide 7 by 3, for example, I get 2 point something. If you do this with integer, most implementations of most programming languages do not return errors, but just floor implicitly the result of the calculation. So instead of 2 point something, you get just an integer 2. And I have an example here with numbers, looking at the time if we can go over it. I think we can look a little bit into it. So what we have here with actual numbers is we have 5 million tokens in the offer pool and 1,000 tokens in the ask pool. We implicitly assume there are 6 decimals here. So that's why this is 5 million and 1,000. So there's an implicit price of 5,000 tokens of one asset for one of the others, right? If I now send in 1 token as the offer amount, that will go into the offer pool, and I do all of these calculations here, then there will be this integer floor division happening here, and you get a 1 instead of a 0. Integer floor division is subtracted as a checked subtraction from the ask amount, and this one is subtracted, this amount. So this is 999, and so on. And then you remain with 1 token. So what's the problem here? The problem is you send 1 token in, and due to rounding, you get 1 token out. But if the price is supposed to be 5,000 for the other asset, this allows the user to just game the whole system and just send tiny amounts, giving again, right? send lots of tiny amounts in and get a ratio of 1:1 instead of 1:5,000. So again, here we have the write-up. I just explained what exactly is going on, but we also include a test case in this example to actually show with the numbers I just showed you how this can be exploited. What are the learnings from this? If you have to round, always round in favor of the product. That prevents skimming, and it's actually then beneficial for users to send smaller, bigger transactions rather than many small ones. If you apply rounding, make sure it's consistently applied to all the state. I gave the example earlier of balances rounding and then the total supply might not be rounded. If it's rounded, always make sure that the same amounts are subtracted from all the different values that are stored in the system. Again, testing of edge cases is very important. In this case here, I think we detected this issue writing fuzz tests. Fuzz tests are generally a good idea if you have functions that accept a huge parameter room, like integers, for example, and you have certain invariants about the outputs, like certain ratios never breaking, the ratio never becomes unfavorable for the protocol. And if you write any code in Rust or in other programming languages that you use integer floor division, be aware of these implicit rounding operations that the language performs. This also applies to floats. If you use floats and you do calculations with them, you might have precision loss. And again, this is implicitly rounding, but many users are not, and many developers are not aware that it implicitly changes the results. Cool. So we looked at these 5 different categories. There are many others. So what do you do with this now? Like, of course, we offer audits, but there's much more that can be done. I already pointed to some of these things, but we believe it's very important to combine different approaches. So an audit can only go so far. We sometimes miss issues, and if someone tells you that they give you a guarantee that there's no issues in their code base, that's probably a lie. So we encourage teams to do internal code reviews before they submit code for audits. Also do testing, as I mentioned before, test happy paths, but also non-happy paths, edge cases. If you have finite state machines, model them. Make sure you have tests for the trace state transitions. Apply fuzzing if you have functions with big parameter spaces. If you have a formal model of your state machine or of your whole system, then you can apply formal verification, which is quite time intensive, but it might be worthwhile if you have a big attack surface. And then, of course, there are audits. There are also audit competitions, not so much focusing on Rust and Go, but they can also be very useful because you get many different eyes and perspectives on the code base. Then bug bounties are important to set up for protocols that have lots of value locked on them, or where the damage can be big if they get exploited. They are kind of a last resort measure, though, because bug bounties are extremely expensive. If someone is submitting a critical issue that could have been caught in one of the other steps, that's quite unfortunate because it's very costly. And also, security doesn't just happen at the point before you release code, right? There's this paradigm shift right now. It's called shifting left. The idea is that in the whole product life cycle, you should ideally catch bugs earlier rather than later, right? If it happens in production, that's extremely costly and damages reputation. Often protocols don't exist afterwards anymore. So ideally, you detect them during release or before you release software. But ideally, you even detect them earlier during development or already when you design the whole system. So CTF is still running until the 17th of July. It does not matter when you submit your replies. So you can even win this if you start on the 17th and submit your issues then. And we have some nice NFTs as a giveaway as a little reward for participants. Cool. That's all for today. If you have any questions, just come to our booth. It's outside in the sun, or in the shadow now. Come over and please follow us on Twitter. Thank you, everyone.